Sì, sì, ho acceso, ho acceso. Ok. Mhm. Okay. Yeah, so let's continue from last time. So we wanted to compute, so we introduced this object and we wanted to compute the expectation value of this object for random unitary circuits. And so we showed that after time t equal to 1, this is equal to 1 minus some f, which is just the OTOC. So out of time order correlator. Yes. Okay, and so we with the usual tricks, we mapped. So we focused on this dynamics, and we showed that graphically this can be represented as a first term, which we argued was equal to 1, and then we have a partition function, which we represent graphically in this way. So here we had all pluses. This spin was fixed to be plus, so this is fixed. Whereas these are variables we're summing over, etc. So here, because of the boundary conditions, we have minuses, and then here we have our operator A0. Again, this is also summed over. Okay, and so this is a four-folded picture. So each gate is actually the average of 4 boxes, one stacked on top of the other. And also, yeah, so the plus corresponds to this, and the minus is this in that picture. Okay, and so now we want to simplify further this object. Okay, so the first observation, yeah, so also let me recall, right, so let me recall that this box is S, corresponds to a projector, which is sum over R. Okay. So the first thing I want to do is to argue that we can substitute the spin S with a plus. And the way we show this is very simple. So in principle, this is sum over all the possible configurations. So in particular, here we should sum over the plus and the minus. But suppose that this is minus. So we already saw that last time that when we have the upper boundaries of this form, this is proportional to delta S minus. So all of these boxes are minuses. And so if this is also minus, because of the way that the triangle or weights work, everything down this line should be also minuses. So you remember we had this rule that S tilde, this is equal to delta S tilde. And so if this were to be a minus, then we would have minus, 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 etc. So applying this rule, the only non-zero weight would be the one where all the signs in the second line are minuses, and so on. But this cannot be, because this is fixed to be plus. So put differently, the weight associated to the configuration with a minus here, it's a 0. Yes? Yes, so B was originally here, but we argued that we could replace B here with a plus. Let me recall what we did last time. So we showed that this gate here, let me call it star. So the gate at position star could be replaced with a plus fixed, and here we had Bx, and here we had a plus. And then I argued that this is exactly the same as plus. And the way to see it is we replace this PS here, so we really only need to show that plus Bx plus is equal to well, actually, we only need to show this. Yes, and sorry, I don't know. Okay, sorry. There was an intermediate step. So I mean, originally, so we could replace that because in the intermediate step, so here we had a minus, and so actually we needed to show this. Sorry. So the simplification we did at this level. So you can go through the derivation, but at the end of the day, the simplification was that this is equal to this, and the way to see it is, again, graphically, because this is minus, and then we have Bx should be equal to, this. But we chose Bx to be such that, so this is equal to trace of Bx squared. This is equal to Q. And so we chose this trace Bx squared to be equal to Q. So this is an identity. Okay, so now we can replace this with a plus. And so we are almost finished. So now taking into account all these fixed boundaries and recalling this, we arrive at the final partition function for the expectation value of Cxt. And so we have I guess let me do an additional time step. Additional step. So we can replace this gate here with now a plus, and so we have plus A0 minus. So here I can replace with plus time the boundary weight associated to this, which I claim is equal to this number. And again, the way to see it is we replace this with an expression for PS. You're going to have a sum of term. Each term is contracted with this, and then using the definitions we provided, you're going to get this result. Okay, so finally, we have this fixed to be plus, this fixed to be plus, and then the other are variables we're summing over, etc. Where the up here is fixed to be minus, so everything is minus except to here. These are free, but there are some non-trivial boundary weights, which we can compute again using these formulas. So let me just give the final results. So the price you pay, in addition to the triangular weight, the price you pay for this to be a plus at the bottom, so bottom, let's say weight of this is equal to q squared, and the weight of a minus bottom is equal to 1. Where here I also reabsorbed the factor 1 over q to the L. So if you put all the factors together, what I claim is that this becomes a fully classical problem of a partition function of spins, where the top boundary is fixed, everywhere minuses except for a plus. In the bulk, you are summing over the variables with triangle weights, and then in addition you also have some boundary weights, which are given by these functions here. Yes? No, it's a. So we can. So no. So here, the thing you have to compute is. Yes. So you have to compute this, okay? And I claim that if you evaluate the sum, then you're going to get this number, where you should use, if I remember correctly, this was, let me write it. This was, so this was 1 divided by q to the 4 minus 1, because it's d squared, where d is the dimension of the gate. So the gate acts on a q squared dimensional space, and the okay. So if you do this, you will get the number. If not, come to me, and maybe it's just a typo. Okay, so we are done. We have our classical now partition function, and now the task is to evaluate this partition function. And so again, the trick is that we can view this partition function as a sum over domain walls, and now the question is, what are the weights associated to these domain walls? So let me take a coarse grain now picture, and first let me show a few configurations that are not allowed. So this is the spin which is fixed to be plus, and we put here at position, star, the gate which is also fixed to be plus. So these are fixed. And now one configuration which is not allowed is this one, where you have two propagating domain walls spreading out. And this is not allowed because this is fixed to be minus. This would be minus, minus, minus. This would be plus, plus, plus. Sorry. Etc. And this will be minus, minus, minus. But the weight of this is 0, because here you will have that this would be minus, but it's fixed to be plus. So it's impossible. And so this weight is 0. And also, let me give you another example of a configuration which is not allowed. So this would be fixed to be plus. This we also, again, fixed to be plus. Another configuration which in principle is allowed but turns out to have 0 weight is this one, because here we will have plus plus. Here we will have a bunch of minuses. But again, it's not allowed because this must be plus. So these configurations are not allowed. So the only configurations which are allowed are those for which this domain wall is at the left of plus, and this C of pluses contains this fixed plus. So just to now walk you through one example of configuration, then we will give the final result. So for example, if t is equal to 4, sorry. Right, so we put the fixed plus here. Then we put so this is a configuration which is allowed, and let me explicitly write down the weight of this particular configuration so that we understand how this works. So first of all, we have that prefactor in front, which is there for every allowed configuration. Then we have the configuration, sorry, the weight associated to this product of pluses, and the weight for the bottom plus is written there. So imagine that these are r. Then here we will have q squared to the r. Then we will have the weights associated to the bulk domain walls, which we compute assigning the triangular weights, which we saw last time. So this is simply q divided by q squared plus 1, which we multiply to 2 times t minus 1. 2, because we have 2 domain walls, and both of them cross t minus 1 links. So this is the final result for the weight associated with this configuration. Yes? Yes? No. At the bottom, yes, so at the bottom here, these are plus, but it doesn't mean that this is fixed to be plus. Why? Because PS has this expression, right? So suppose that S and plus are not orthogonal. So minus, minus, plus, plus, this is, rainbow times, and this is q squared. So they are not orthogonal, okay? And this is why, even though these legs are plus, this S is not fixed to be plus, it just has a different prefactor. It's only for the top that if these are minuses, then that, and the way to see it again is this one. So if you plug this expression into the top, you see that this is not symmetric bracket, okay? And so they're not orthogonal. So simply you will have different weights if the bottom is plus or minus, and the weights are computed here. So this is the weight for this configuration. Now this is a fully, yes? You wanna how I arrived here? This one? Yes. So this is the usual bulk weight associated with the domain walls, and it's exactly the same one we had before. So given a configuration, in order to get the weight out of this, you should multiply all the triangular weights. So imagine this is maybe infinitely large. We start by multiplying. Okay, so every time we get a triangle where all these signs are the same, we get a 1. You see, because if they're all the same, it's just 1. So we don't care every time we have homogeneous signs. But then here, at the boundary of the domain wall, we get plus, plus, minus, which is non-trivial, and this gives us, so this, it's the weight I wrote last time. This is q divided by q squared plus 1, right? So here right here we have 2 equal and 1 different, so we get this number. And so you can see that the only thing which really contribute is across this domain wall line. So how many are they? So this is time equal to 4. We have 1, 2, 3, so t minus 1. So this is for this line, and this is for this line, and therefore we have this one. Okay, so now this is a sorry, it's a fully StatMech problem, which is now completely defined, and it could be. I mean, it's not simple because you see, you have to count domain walls, and then depending on how these end up, you have different weights. But it could be solved analytically. We will not do this. Let me just give you the reference where you can find the analytic solution. And again, it's this reference I already gave last time. Sorry. And so in the case you're familiar with different fields in StatMech, this pertains to a field which is called a lattice path enumeration. And so this can be solved using a trick which is reminiscent of the image charge you have in electrostatic. So it's not, I mean, it's something which is standard if you already know the literature, but it's a beautiful piece of mathematical physics. So let me just give you the final result, and then we will finally interpret the result. Yes? Just here with f of t. In f of t, you have a 1 over divided by q to the f. Yeah, yes. So here I reabsorbed into the, I mean, I reabsorbed into the weights. So you see that the bottom for the weight now is 1, but here I computed it and it was supposed to be q squared. So what I did, I reabsorbed this 1 over q to the L into the bottom. Okay. Exactly. Okay. So I try to arrive less painfully, as less painfully as possible to the final result. But I think from here, either already from the blackboard, or maybe getting back to the original papers, I think now it should be clear how to reconstruct the calculation. So the only thing which is non-trivial and we haven't done is how now to evaluate the partition function. But this you can take as a black box. It's a StatMech problem which you can solve with the standard techniques. Okay, so now we give the final result. So we introduce to where we are assuming x plus t odd, and x and t are those appearing in the definition of C xt. And we also define p to be 1 over q squared plus 1. So now the partition function can be evaluated at finite x and t, and the result is this one. If you have a problem reading this in the back, please let me know. Okay. Okay, where Okay, so this is the final result. So it's an elementary function. So we first define this, which you see this is a sum of a probability distribution. So this is a probability distribution. If this ran from 0 to n, this would be 1. So here we're simply summing up to some point. And then that is the expression. So in order to understand this, let me now simplify this in the limit of large space and time. So this is for finite x and t, it is what it is. But now we are interested in a large scale description where this now simplifies and we can understand it based on a very simple picture. So, yeah. So in order to simplify, we use that when t is very large, we have so the two terms are the same up to subleading terms. So we can just sum the prefactor in front. And so we get so this already is a bit simpler. And now we do a further simplification. And we use the fact that, so this is a binomial probability distribution. We use the fact that when we have a large number of samples, then this can be approximated by a Gaussian distribution. So this is standard. It involves expanding the binomial using Stirling's formula. So if you do this property in the limit of large C and large X, you find that this is almost equal to the following function, which is our final result in the large space-time limit. Okay, so somehow it takes longer than to write the solution than to state the problem. So we actually, the only thing we need is to, so I mean, the point is that this expression is valid if t is large compared to 1, but actually it's only meaningful if both t and x are large. I mean, we will see this in a minute. But for the moment, I mean, here, this you can approximate, I think this expansion holds for t much greater than 1. Okay, so now we have defined okay, and then this is the error function. Yes. Okay. So, and finally, let me plot this thing, and then we will discuss it. And let's see. Okay, so this is our final result. So this is just a plot of this function, and let us interpret what this means. So you see that this is it's a snapshot for a given time. So if you were to visualize this in a 2D plus one dimensional space, you would see a front which spreads out, and inside of the front, this quantity would quickly become equal to 1. Also at the front, which spreads at velocity vb, you have a broadening of this light cone, which is diffusive, so proportional to square root of t. And here, the tails, they are exponentially decaying, but differently from what could have naively expected from a naive generalization of the Lieb-Robinson bound, this decay is not exponential, but is it's actually Gaussian. So here it's right. So at the leading term, this tail is decays as x to e to the minus x squared, not e to the minus x. Okay, so now what I want to do is to interpret this result now based on a very simple picture, and I want to argue that these features are what you would expect from a completely chaotic dynamics where you really have no structure. And in fact, this shape for the function c x of t and for the OTOCs is sometimes taken as a definition of quantum chaos or quantum scrambling. Yes?
So this behavior, like the Gaussian behavior, like Gaussian,
yeah.
seems to suggest that this kind of system, like the bottom case is too weak for this kind of system. Like the bottom case will allow for a decay not as much.
No, but so if you look at how we define the butterfly velocity, this is consistent with that because we define it by taking the log of this divided by 1 over t and then taking the limit. So this is still consistent. I just wanted to point out that when you have the Lieb-Robinson bound, here the bound tells you that this is going to be exponentially small, but we do the calculation for this state-dependent quantity, and so we find that this is now e to the minus x squared. Yeah, it is much stronger, but you, as I said, you would expect something much stronger because this is a state-dependent statement, right? Yeah. Yeah.
What we talked about small t, what we did in the last section, presented what happening for small t, because we had
Yeah.
the beginning behavior and reaching the steady state. Here, it was called
so I mean, so the small t usually it's highly model dependent, so it's not considered to be particularly interesting. I mean, honestly, here I think the best way to visualize what happens at small t is to so this formula is exact also for finite t, and I would just study this and see what happens. But I mean, some limits are obvious, right? If the points are separated to a distance which is larger than the geometric light cone, then this is simply going to be 0, and so there is a small, non-trivial region. But I mean, what you can see numerically is that you approach the asymptotic form very, very quickly. So already perhaps t equal to 4 or 5 is enough to approach this asymptotic form. Okay, so before giving this heuristic explanation of why we should have expected this for chaotic dynamics, let me mention that there is a conjecture that in fact the shape we have found here for OTOCs is actually very general. And fits a general form which with some free parameter is expected to hold very generally, so both for chaotic and non-chaotic dynamics and in higher dimensions. And the form which has been conjectured to hold is the following. So yes. So let me give you 2 references where you can find a discussion about this. And the second reference is okay, so first of all, you can see that this fits our form if, in this case, we put alpha equal to 2. You can simply substitute and see that this is consistent. And you can also rearrange this into, in a compact way in this way, where lambda v is some function of the velocity. And this is always, it's often stated to be this coefficient to be a velocity-dependent Lyapunov exponent. Now, I do not want to enter into this, but Lyapunov exponents are something which is very well known and studied in the classical theory of chaos. And so you can recover even in local quantum circuits without a proper semi-classical limit. You can still recover a notion of the Lyapunov exponent. It's just that it's going to be time velocity dependent and it's going to have this form. But also there is an additional subtlety in that this form, sorry, I didn't say, but this holds right outside of the light cone. So indeed, this is consistent with our definition right outside of the light cone, because you see this becomes exponentially small for v larger than vb, which means that outside of the light cone, this is going to be smaller than 0. And so this expression, when you have local dynamics, doesn't really make sense inside of the light cone, because it's, or you could say that inside of the light cone for local dynamics, this is going to be 0, because it's not exponentially decaying and it's not blowing up inside of the light cone. Whereas when you have something like SYK model, then you can, you can give, you can say more about this type of Lyapunov exponents. Yes.
What is the typical scale between V3 and the velocity again?
So the general relation is that this butterfly velocity should be smaller or equal than the Lee-Bromison velocity. Then typically they're, I would say, the same order of magnitude. But I believe you could probably make them as separated as you want by maybe choosing some weird initial state, some weird stationary state, I guess. Yeah.
Yeah, so because it's circuit, you have an exact light.
Yes, yes.
Would that be on the figure?
Yes.
Would it be v equals 1? Or?
So in this case, yes. So the exact light cone is exactly v equal to 1. And so here at this point, this approximation will not be good anymore. Instead of being exponentially small, this will be 0, exactly 0. Yes. Yes, exactly. Yeah, and you can see it from here, right? From Q.
So does the inside of the light has is it always expected to be 1 or
Yes, I will do it now, and I will argue that this is what you should expect for chaotic dynamics, and this is taken to be a signal of chaos.
Sorry.
Yeah. Yeah.
This expression is valid for what?
This one?
Yeah.
Okay, so here we had an exact calculation, and this is what you get, right? But then I was saying that it is conjectured, and you can see a discussion about this in these two references, that for arbitrary, let's take for simplicity one-dimensional systems, that if you now compute this function c x of t, and you look at it at this position, taking v, let's say, slightly larger than the butterfly velocity, you will always end up in a form which is, in an expression which is of this form, where the free parameter here would be alpha. And this is true also for dynamics which are non-chaotic. For example, you can compute this for, I believe in this paper, they compute this for even non-interacting dynamics where you have no chaos, but still you have a butterfly velocity. And for example, in that case, I think alpha is some 3/2 number. So this is what I meant. right outside of the light cone, let's say.
Yeah, but not only for quantum systems.
No. This expression is conjectured to be general, and it's, if you want, then this alpha becomes a probe for dynamical properties. Then it's not crazy to imagine that maybe if we restrict to 1D with a local interaction, then we can claim that integrability means that alpha is going to be maybe 3 or 2 or something. Yeah.
About these statements
Yeah.
about quantum chaos, but usually people in quantum physics describe also quantum chaos based on the spacing between energy level, which scales up a certain function of the system size. Is there any way here to reconcile this with this notion of energy levels, since we have random matrix theory?
Right.
Or is it two different
Right.
definitions of quantum?
Yeah, this is a very good question, and of course it's very natural to ask. Okay, so here by construction we do not have a Hamiltonian, so we cannot address the question of level statistics. However, the claim is that whenever you have a chaotic Hamiltonian, where you define chaos in terms of the spectral statistics of the Hamiltonian, you would expect that the calculation for the OTOCs would give this result. So the conjecture is that if you have a Hamiltonian, which you would consider chaotic using this standard definition of chaos, then you would find this chaotic behavior. And indeed, so usually people when people talk about OTOCs and also other quantities, they sometimes not refer to chaos but to quantum scrambling, which to me it's something slightly different. But the idea would be that this pertains to quantum scrambling. Then chaos, it's a statement about the spectrum, and then you simply say that scrambling and chaos they tend to coexist. Yes. But okay, so also let me tell you that I wanted to do this today, but perhaps going to be the next lecture, that then you can also investigate circuits where you don't have disorder, which allows you to study Fouquet dynamics, and there you have a spectrum, and you can study spectral properties like the spectral form factor. And what you find there, there is a class of circuits which is called one unitary, which allows you to then study both, and you see that they really coexist when you study them both. Okay, so now I think I should stop here, and then yeah.
Okay. Other questions?
Yeah.
Is there a classical limit for the equation?
A classical limit for this?
Yeah.
Yes. So classical limit is something which has been very well studied in certain quantum systems where you have a natural large n expansion like SYK, for example. And so it is discussed in these references. I didn't want to touch upon this, but here there is no natural semi-classical limit because there is no large n parameter. I just wanted to make the connection that even here there is still a notion of Lyapunov exponents, just that this is velocity dependent, which is something that you don't usually have in classical theories.
Isn't large Q similar to large Q?
I mean, so in a sense, but like for example, you have a semi-classical limit if you have a chain of SYKs, and then each dot is an SYK. But then you have to be a bit careful with the quantities and how you identify things. So also this is something I mean it's at the boundary of what I know. So maybe let me read a bit before answering to you. Yeah.
Okay. Other questions?
Yes,
Yeah.
I missed the point. We started with this discussion because I wanted to say that butterfly velocity is like a state dependent velocity.
No, so we started discussion because I wanted to give a overview of all the physical parameters that describe a chaotic dynamics. So the idea is we're using this, so we have defined a set of models which are random circuits, but then we want to use that to extract some physics of generic chaotic dynamics. So for the moment we're interpreting this as a useful toy models that allow us to extract information and learn some phenomenology of chaotic dynamics. So we have studied the behavior of entanglement. Then I also wanted to study how operators grow, and I wanted to study in some detail the properties of this butterfly velocity. And I want to do this because then at the end, I want to recollect all this information into entanglement membrane theory, which I will argue holds more generally to also more general theories. So for the moment, you should take this as a study of OTOCs, which we have solved in one particular model, but you should expect that this happens if someone comes to you and gives you a Hamiltonian without any particular structure, you should expect that the OTOCs behaves in this way also for that model. Where, of course, the butterfly velocity will not be q squared minus 1 divided by q squared plus 1, will be something else, but that will be the input if you want, and then this is what you would get at large space-time scales. Yeah? Yeah. Also, yes, please.
Here considered a very specific distribution to take the unitary matrix into, which is the Dehar distribution.
Yeah.
Would the similar result hold for different kind of distribution of these?
Yes, okay. So, of course, you would expect things like the butterfly velocity number to be to change. Again, unless you fine-tune this probability distribution such that it has some maybe conservation law or some fine-tuned property, you would still expect this to be a generic and chaotic dynamic. So you would expect to recover the same phenomenology where you just simply change these input parameters. But so far, I mean, this is not a statement about universality in the classical RG sense. So these are not universal quantities, but this gives you a guidance to what you should expect when you have some chaotic evolution. Because otherwise, I mean, the best you can do is you take your Hamiltonian, you run it on your computer with a D, you stop your simulation at 18 sites, you get some, noisy result, and it is very useful to have an intuition of what you should expect. And also, I mean, after the break, I will show you how this you could have inferred from really a simple picture. But I think it's very useful, whatever you do in your research, to have this kind of intuition based on this very simple model. Yeah, thank you. Just before continuing, so let me emphasize a few limits and inequalities which are consistent with what we said. So the first one, as Jeroen said, so in our circuit we have a maximum velocity which is enforced by the geometry, which is 1. So this is smaller or equal than 1. And also we somehow claim that the butterfly velocity is the fastest way in which we can propagate the signal. So you would expect that the purity velocity is smaller or equal than VB. And you substitute the previous expression we have, you can see that this is indeed verified. And so if we put a few things together here, we had V butterfly velocity is more equal than V and smaller or equal than 1. So one question was, can we find circuits now where somehow they all collapse to 1? And of course, if they all collapse, then you will not have any diffusive broadening. So somehow it will be dynamics as, I mean, it gets chaotic as fast as it can. And the answer to this is yes, and we will see later, perhaps, or next time. And these are dual unitary circuits, which are not random circuits, so they're Floquet dynamics, which in some sense are the maximally chaotic dynamics you can have. Okay, so now let me give you an intuition of how we can understand that plateau in the bulk, which is equal to 1. And so let me now take a very simple picture. And so we imagine now that if we start from some operator here at position 0, we imagine that this operator will simply spread. So the support of this operator will spread at a velocity which is VB. So at large times we have this. And then within this region, it will be a random operator. So of course, this is not what happens because we have our dynamics, so there is some structure. But what happens if we really take this stupidly simple picture? So in formulas, what we can imagine is that at time t, our unitary operator will have this decomposition. Yes. So here I'm assuming VB times T to be even. I mean, it's not really important, but just so that the formulas make sense. Okay, and so let me define L to be VB T plus 1. So we're saying that this now is equal to L. Okay, and this is already an approximation, because here we're only assuming that the support of this will grow into a sum of operators which are strictly supported over the butterfly velocity Lycon. And this is not true, because you will also have strings propagating all the way to the Lieb-Robinson Lycon. Okay, and now we assume that this is completely structured, so we assume that this is somehow a random number, and the only constraint we need to satisfy is that okay, so let me take, for simplicity, A0 to be a Pauli matrix. Yes, so then this is going to be 2DL. So here I'm assuming A0 equal Pauli and A0 dagger A0 equal to the identity. Okay, so this is something that must always be true because here this is U dagger cancels with U, so this is an identity, so this must always be true. So we can pick this randomly, but their normalizations should be such that this condition is satisfied. And so we can, we ask that the absolute value of this C is equal to 2 to the minus L. So we take them random, but spread uniformly. So there is no preferred string. And so put differently, we're just saying, okay, these are a random number with the only constraint that this normalization is conserved. And you can show that if you put this here, then this is satisfied. Yes, so I have questions. Yeah. Feel free to.
I have two, like, because usually you have B operators, so you have to choose a B here for applying.
No, so yeah, for the moment, no. So for the moment, I'm just focusing on, in the Lieb-Robinson velocity you have, sorry, the butterfly velocity, you wanted to compute this, right?
Oh, yes.
So there is one which evolves with time and one which is fixed and used as a probe. So here, now I want to have a very simple heuristics for explaining that plateau which is equal to 1. And the heuristic I'm going to give is that morally, this is going to evolve like a strict Lycon inside of which is completely random. Yeah? Yeah?
Sorry, like the trace equation you have, that's a constraint as well? It's under normalization?
No, so here I'm saying, okay, we want to pick this randomly, right? But then I cannot pick all of them to be 10 to the 16. Why? Because if I pick them to be 10 to the 16 and I compute this object, then I will get a number which is stupidly large. And so what is the constraint I have to satisfy at least? So the constraint that I have to satisfy is that the norm of this should be equal to the norm of this, because I'm imagining this is still a unitary evolution, so this must still apply. And so if this is a Pauli matrix, this is 2 to the L, right? And so I'm saying that one way to do this, to imagine that this is a random number, but with the expectation value, so norm of it to be 2 to the minus L. Now, I'm not specifying who these guys are, and it might even be that this is, you cannot realize in practice, but here I'm really doing a heuristic, I mean, really the simplest way we can try to understand this picture. So from here on, not going to be rigorous in any way. Just I mean, for consistency, they show that this gives you the correct number. Okay, so here I have so here I'm assuming that A as the form on the top, and then I'm evaluating this. So when you expand, you see that this is going to be a sum of the coefficients, because cross term will vanish. If this is confusing, we can do this explicitly, but it should be an easy calculation to show. So then, I mean, let me do it so that this is crystal clear. I mean, so there, what I'm doing is I'm doing trace of the sum over alpha. Then here I have this string. And then here the same. So here there is a dagger. Here I'm using Pauli matrices because we're assuming everything, I mean, we're assuming we have q equal to 2, so we have qubits. So now we expand the sum, and we are using that trace of sigma gamma 1 sigma gamma L is only non-zero if all of them are the identity. So delta gamma 1 0, delta gamma 2 0, delta gamma L 0, where I'm using the convention that, again, standard is the identity, sigma 1 is sigma x, etc. Right? So it goes up to 3. So we have 4 Pauli matrices. The first one is the identity, and then I'm using the simple identity, which also is trivial. So now using this formula, I want to expand this. I'm going to get a sum over 2 sets of strings, and the only ones which will not die are the only ones which will not die are those where all the strings coincide, right? Because if they do not coincide, then the product of 2 will generate an non-trivial Pauli, so that will be 0. And so if I call now this star, then star is going to be equal to a sum over all possible sequences of L Pauli matrices of C alpha squared, and then here I have a trace of the identity, right? Because when alpha is equal to beta 1, sigma alpha dagger, sigma alpha is the identity. Okay, so I have this. Okay, so this is the factor 2 to the n that we wanted. This, because of our choice, it's going to be 2 to the minus L squared, because there is a squared. And so we simply need to count how many strings of L Paulices we have, but each of them can be 4 things, 1, 2, 3, 4. And so we have 4 to the L of them. 2 to the minus L to the 2 times the n. Okay, so this simple calculation shows that this assumption is at least consistent with this minimal constraint. Okay, and so okay, so now we evaluate this. We want to evaluate this where Bx is some Pauli matrices as position x. So because of our choice, this is going to be 0 if x is greater than L over 2. Because we are assuming that this has no support outside of the butterfly light cone. And so you have something non-trivial if x is inside of the light cone. Okay, and so what is this thing which is non-trivial? So suppose that Bx, for example, is at position 0, and so it's some Pauli x, right? Sorry. Yes, Bx, sorry, it's some alpha at position x. Okay, so this commutes with exactly half of the strings, and anti-commutes with exactly half of them. Because this, for example, it commutes with, so we have to take the anti-commutator of a string, sigma beta 1 minus L over 2, sigma beta 2, sigma with this. Right, so I'm plugging for this, I'm plugging the expression above here in this commutator. This becomes a sum. The commutator is linear, so then the only thing which is non-trivial to evaluate is this one. And you see that this either commutes or anti-commute with the string, and the only thing which you have to care about is the Pauli, which is at position x in the string. And so there are 4 possibilities for the Pauli matrices at position x. It's either identity or sigma alpha, and in which case commutes, or it's one of the other 2 options, in which case anti-commutes. So now you use this information, and then you just take the square root of this, and you count the number of zeros and non-zero that you get. Of course, when this anti-commutes, you get the same number multiplied by 2. And so if you put everything together, and this is just a trivial counting problem, the number that you get in the end is this one. So this is something which is easier done than said. Okay, so this is the factor that comes from the coefficient C absolute value squared. This is the factor from rho beta equal to 0. It's just a 2 to the L. It's just a normalization factor. This 1/2 over 2 is the number of strings for which this commutes. And this 4 comes from the fact that the commutator gives you a factor of 2, because when it commutes, it's like multiplying by 2 with the correct Pauli matrices, and then when you square, you get a 4, and so this gives you 1.
Before or after the parentheses little L?
Sorry?
The L, is it inside or outside?
I don't know. Sorry. It's yes. So you have 4 to the L strings, and then you have half of that number. Okay, so maybe I lost you in the details, but it's something that you sit down, you do in 2 minutes, and it's just to say that if you now have this super naive picture of one point operator that spreads uniformly, then the answer that you get is close to the original to the actual result. So you will get something which is a sharp light cone at VB. So this is one. So you lose information on the broadening, but otherwise it's a pretty accurate picture, right? So this is why the fact that this CXT becomes 1 inside of the light cone is associated to a dynamics where you lose information on the structure inside of it. Because if you have a model where you have 0 information, you somehow recover the same result. Yeah.
Okay, so the claim is that basically you get like a uniform distribution over Pauli strings.
Yes.
On
Yes.
Is there an obvious connection between this and, say, R measure on input space of size 2 to the n? Is it the same thing?
So I guess the corresponding thing you would do here is you take one unitary u of size, yes, small l, and this would give you the same, yes. So another way to see it is instead of having, right, so here, and then you replace this with the identity. This is another way to get the same result, yes.
So
It is the same thing, yes. I guess this would give you the same thing, yeah. Yeah.
For this, at the top you wrote that the total interval was of size VBT. Here you say that it's half the interval, which is VBT. How do you define really VBT?
No, so the whole interval is VBT, but I start from 0, right? So then this is a VBT over 2, right? So
This is my question because I would expect information to travel at a speed velocity VB in both directions at the same time. So I would expect
sorry, yeah, no, you're right. Sorry. No, sorry. And no, so here, yeah. Sorry, that VB is twice as much, yeah. Okay. So, okay, so this motivates why people, when they talk about OTOCs and they talk about chaotic dynamics, they say for chaotic dynamics, OTOCs should go to 0. Okay, so finally, I wanted to, in this last part of the lecture, I wanted to introduce this entanglement membrane theory. So somehow now you can forget about all the technicalities, and we have this large-scale entanglement theory, which I believe it's useful, again, as a guiding principle when you approach entanglement dynamics for a system for which you have no prior knowledge of conservation law or particular structure. Okay. Okay, so now let me start again from the purity calculation just to set up the discussion. So this is going to be a brief discussion. So I think in 15 minutes we'll be able to do everything. So now we have our one-dimensional system. So here I'm taking one dimension for simplicity, but in fact this entanglement membrane theory is argued to hold also for higher dimensions. And in some cases this also be derived in the context of holographic field theory calculation. So it's quite general. Okay, so for random unitary circuits, we were able to derive something like this. So we have a purity, the average purity, we're able to write it as a sum over domain walls. Right, so here we have some boundaries. And each domain wall has a weight associated to it. Now, of course, in this case of random unitary circuit, everything was so simple that we could actually see this at the microscopic level. But now, the idea is that it's useful to now cross-grain and have a description which is independent of the microscopic degrees of freedom, which we might think holds also when you don't maybe have a quantum circuit, but even a Hamiltonian dynamics. And so what you do is you replace this sum over microscopic paths with a path integral over continuous curve. Okay, so this is the idea, and quotes. So you shouldn't be interpreted this literally. But this description makes sense if we take now the limit of t goes to infinity, subsystem goes to infinity, and we take the ratio of the two fixed. And now, when we write this, it's, as usual, when we introduce some path integral, it's not enough to simply replace microscopic curves with continuous ones, but one also has to introduce some entropic factor. Because when I draw a line like this, then there can be many microscopic lines that are associated to the same continuous line. And so the proper way to write this is to write this as a path integral. And here we'll have a free energy associated with the path gamma, where here I put a 2 to emphasize the fact that this particular free energy corresponds to the fact that here we're computing the Rényi 2. Okay. So for the case of the Rényi 2, again, we have a concrete microscopic model, so this discussion could be made more formal, although being rigorous here is not the goal, but at least the level of the Rényi 2, this could be made more formal, and so this will have an expression of this form. Yeah, so you can write as an integral over the t of a cost function associated with the velocity of that curve. And we saw a manifestation of this at the microscopic level when we had the mean cut picture, because this is simply a sum over the small time step time the cost of that curve. And in the mean cut picture, this is simply the length of the curve. Right? So for the mean cut, epsilon 2 of, this is just the length, again, with quotes, but just to convey the idea, it's the length of the curve. Okay, so the entanglement membrane theory posits that something like this you can write even for high Rényi entropies and for the phenomenon entanglement entropy, even if it might be very complicated or perhaps impossible to get the exact expression for this cost function. So the yeah.
Is this occurred in a plane, in space-time?
So for here, I'm restricting to 1D. Okay. So this curve lives in the space-time, say in the space-time 1+1 dimensional, right? So I mean, for the moment, so we know from the microscopic theory that this curve has some constraints. Sorry, say it again. Yeah. Yes. So, of course, you could parameterize this in different ways, and then it will just give a different free energy, right? The time, so this dt is the physical time, because it's more convenient to think it like that, because if you do, then there will be a natural interpretation for the epsilon of u. Yes, gamma dot is a vector. So actually, in this space-time curve, it's actually, if you want the absolute value, so it's actually the derivative. So in this simple case, this is it's the derivative of the curve, so it's a number. So maybe this is confusing, but so what I mean. So we saw in the previous class we saw, so if this was A, we saw two possible types of domain walls, so of course, right? So here, this would correspond to a velocity v equal to 0. Sorry, v equal to 0. So I'm associating to this curve, which is straight line, a number,
which is what I call velocity, and it's equal to 0 in this case. And here I'm associating to this curve a number, which is, again, the slope of this. So here, the notation is confusing because I probably wanted to make this more general, and I failed to do it, but it should be clear what I mean. So you have a curve, and this is going to be a function only of the slope of this curve in 1D, 1 plus 1 dimension, okay? Yes.
Here you are writing an integral on one curve, while you have two boundaries for this curve. So is it really an integral on the surface? So two curves.
Right. So here, again, it's a poor notation, but this gamma really means it's not necessarily a connected curve. It's the sum of segment separating your region A from the rest. Okay. So again, this is for 1D, but then you could define this in higher dimension, and so you should replace then lines separating your region with a membrane, and this is why it's called the membrane theory. Okay, so now, okay, sorry. So here I forgot to say something. So here this is a path integral, but then we're taking the limit of the scaling limit, right? So now we're taking the limit of large A and large T. And so the intuition is that now this will be dominated by a saddle point curve, which will minimize this free energy. So the intuition is that now this is going to be some F2 of some saddle point curve. And so at the end of the day, we can compute the entanglement by looking just at the free energy of the optimal curve, which separates your region with the rest. So again, in the mean cut picture, the optimal curve is the one which minimizes the length of the curve. And not only that, but the cost of the curve is actually the length of the curve. Okay, so now we would like to argue, so this is not going to be a rigorous piece of the lecture. I want to argue what we should expect for a general cost function. And now for the rest of this lecture, I'm not going to focus on the Rényi 2 case, but more generally we can take the any Rényi, and in particular the most significant one is the entanglement entropy. So we will now focus on the entanglement entropy. Yes.
So in the subject case, you basically have all curves with the same length, right? And they were just empty. If you exclude this triangle.
Sorry, say again.
Every curve that connects the two boundaries.
Yeah.
Was just a length t in the subject case.
It's just sorry, I didn't hear it.
Just
A length. Yeah.
So here you're associating different weights.
So here, I mean, here you should have. So the idea here is that you should start from the circuit, but then at one point you should forget about the circuit. So the idea is that we want to make something more general about the circuit. Everything we do here, we have an immediate correspondence to the circuit. So you remember that, for example, when we have this interval A, and t is sufficiently large, we had two ways of separating, right? One was this, but then we also had, curves doing this. So the point is that when you have this sum over discrete paths, of discrete domain walls, for a given set, for a given macroscopically large curve, you have many microscopic realization. So in this sum, you want to replace this with the path integral over the curves. So now this will become the curve. But not only you have the energy, which is the triangular weight, you also have the entropic factor, which is how many way can I represent this smooth curve at the microscopic level with individual trajectory. And this is really the standard thing you do when you introduce path integral in many different statistical mechanics situations. So it's nothing fancy. And I think if you have in mind the StatMech model, you can almost have a one-to-one correspondence between these formal steps and the lattice partition function. Yeah.
And the statistical observables can be obtained using such path integral. I mean, this one, such as the other one you've done afterwards, can we then expect the scale law you obtain around the butterfly velocity
Yeah.
to be obtained using, for example, some large deviation theory around these different paths?
Right, so this is a very good question. Yeah, so that is what you would expect, right? When you introduce this kind of formalism, then you would expect that large deviations tell you something non-trivial. But I will absolutely not do this in class. And I think, I mean, to my knowledge, this hasn't been done yet in the literature. All right, so now, okay, so what should we expect for that epsilon 2? Okay, so here now I will put a v, which again, for the 1D case, this v is the slope of the curve. And so this epsilon will be an epsilon of a v, an epsilon of the slope. So here I'm plotting what we would expect for this function, and which also determines the saddle point of the calculation. So let me skip some steps, and what I would like you to believe is that a reasonable form for this cost function is this, where importantly this epsilon of e is greater than 0, and this makes sense because this should be a cost function. If this were a negative, then what we do wouldn't make sense. But also, for consistency reason, it should also be that this is the second derivative is greater than 0. Otherwise, again, you can run into inconsistencies. Okay, then you should expect that your epsilon of v goes from some maximum and minimum velocity. And then going back again to our quantum circuit model, the natural candidate for this maximum and minimum velocity is the butterfly velocity. Now, there is a natural candidate here that you could have put, and that would be the Lieb-Robinson velocity. But then you can argue in a quite precise way that this is what you should expect. So that this epsilon of v, the maximum velocity that this can take as an input, is this butterfly velocity. Okay, so then finally, here you can ask what is the value of epsilon v at the value of velocity v equal to 0, and this is something we can actually already infer. And to do that, suppose you have your bipartite system. So here you will have region A, here you will have region B. And then you want to compute the entanglement, assuming that A is very large, B is very large, and is large compared to T. Then by symmetry, it's natural to posit that the optimal curve should be the straight line here, because it wouldn't make sense that it's some other curve. So maybe this could be degenerate, but this for sure should be an optimal curve. And so the cost of this should be equal to epsilon 0 times t times SE. So now I'm starting using this theory. So I'm saying that according to this theory, the entanglement is going to be given by the saddle point of some free energy that maybe I don't know. But this free energy depends on it's an integral over my curve of the cost of that curve. And in the large space-time limit, this path integral can be evaluated via saddle point, so we need to look for the optimal velocity. And once you have the optimal velocity, then the free energy is simply going to be given by an integral of dt times epsilon of that optimal velocity. So if now we use the theory here, and we also assume that the optimal curve is the straight line, then this tells us that the entanglement of A is going to be given by this integral, which in this case is trivial because this is a straight line. So T times SE equilibrium, which is given here, times epsilon of the velocity, which in this case is 0. Okay, sorry, one thing which I forgot to say is that this S equilibrium in our case for infinite dynamics is the logarithm of the local dimension. So it's the entanglement of a equilibrium subsystem at very large times. So this is what we would get, but we also defined the entanglement velocity to be the rate at which the bipartite entanglement entropy grows.
Sorry, I'm not understanding. Are you saying that the optimal velocity is 0?
So this is reasonable by symmetry, okay? Because the bipartite entanglement entropy should be invariant under the two. And so, I mean, so it's reasonable at least to conjecture that this is the case. And in fact, you can argue even more precisely that it should be a straight line in this case.
So you have a minus. We are taking the maximum.
I have a minus, yes. Yes. Okay, sorry. I'm very sorry, okay. Actually, I mean, this sum, if you remember, this was not the entropy, this was the purity, right? So then, if you want the entropy, you have to take the log of this, and the log of this is this f. So then everything is consistent. And then when you take the log, you have this. Now let me check the signs. But with the minus, you take the minus, so I think now everything is consistent. Sorry about that. I was sure this was going to be confusing, and I also didn't perform well. Yeah. Yes. Okay, so for the mean cut picture, this one, yeah, so this will trivialize. It will be a flat line. No, it should be the velocity. So, let's see. No, okay, sorry. No, it shouldn't be a flat line. It should be a cusp, I think. So let me. Now I'm a bit tired. So let me come back to this last time. But it trivializes in large Q limit. Yeah. So the claim is that now we, in fact, I mean, there is a way to compute this epsilon of V even for random unitary circuits at finite Q, and this is the shape you would get at finite Q.
And when Q goes to infinity,
it trivializes, but not enough. I mean, it doesn't become flat. That's not correct. I think, but this I have to check. It should become like this, I think. Yeah. Yes. No. Again, it was his question. So again, sorry. Let me maybe come back to this in. So okay. Let's see. So is it at least clear what I'm trying to do? More or less. So I would like to have a cost function, which by only looking at this cost function and deciding which is the curve with the minimal cost, I can separate my region from the rest. Now, in principle, this cost function can be whatever, but there are a few things which is reasonable to expect. So the first one is that this cost function is larger than 0 because it's a cost function. I should pay a price to separate my region with the rest. And then I'm also telling you that one thing that you should want is this, and here you're trusting me. Now, then the question, okay, I have this epsilon V, how do I use it? And I'm claiming that you should use it in this way. So if you want to compute your entropy, you should select the optimal function, and then for example, in this case, you take the log, you should integrate the curve over this optimal function. So for the moment, I'm just trying to convince you that this is consistent with, so if you have now this bipartite entanglement, and you choose this, where this value here is VE, so epsilon of 0 is equal to VE, then this would give you the correct result. Let's see. So first of all, if I assuming this form, is it true that this is the optimal cost? And you can see that it is, because if you do now a curve which is like that, then the cost of this function, sorry, the cost of this curve would be higher based on this curve, which is strictly concave. So if I now assume this form where this is v is equal to 0, the optimal curve that I get is this, and then the entanglement that I get is exactly the one that I want. So I guess I will stop here, and then next time I will try to do this more carefully and finish the story. Thank you.